ID number 131. Are you there?
Yes, sir.
Okay. ID number 132,
Yes, sir.
133,
Yes, sir.
134,
Yes, sir.
135,
Yes, sir.
and 136. Typo in the ID number on the slide. Anyway, 136. Are you there? Okay. Fine. 5, 6 present anyways. Let's put it. Okay. Let us continue with our discussion on vector spaces. So we defined what is the span of a subset of a vector space in the previous class, right? Kandarp, can you please mute yourselves? Okay, thank you. So let us just revise or revisit this definition. If we have a vector space V with us and let us consider a subset containing n elements, then span of this set U is nothing but the set of all possible linear combination of elements from U, right? And of course, if U contains infinite elements, then as we discussed, right, on the vector space, we do not have a good definition of infinite linear combinations. And so therefore, in case this subset U has infinite number of elements, then span of U is defined as the set of all possible linear combinations of all possible finite subsets of the set U. Okay, that is how we will define span of an infinite set U. Moreover, towards the end of the last class, we also proved that span of any subset U of the vector space V is going to be a subspace. Okay, so are there any doubts here? Okay, I take that for a no. Let us now define, using this span, something called a spanning set. Okay, so if we are given a vector space V, and if W is a subset of V, such that span of W is exactly equal to the vector space V. In that case, the subset W is what is called a spanning set of the vector space V. Okay, or we'll also say that W spans V. Right? I hope this should be easy enough to understand. And using this definition of spanning set, we now define what is called a finite dimensional vector space. Okay. Right. So we say that the given vector space V is finite dimensional if, okay, if there exists a set which has finite elements and it spans the vector space V. Okay, so it doesn't say that all spanning sets have to be finite, it just says that there must exist at least one spanning set which has finite number of elements. Okay, in that case, the vector space becomes a finite dimensional vector space. Of course, note that we have not yet defined what do we mean by dimension of a vector space, but we are defining the phrase finite dimensional vector space over here. Okay, so we as of now do not know the answer to the question what is the dimension of a particular given vector space, but we do know whether a particular, what does it mean to say that a particular vector space is finite dimensional. Okay, and of course the complement to this is an infinite dimensional vector space in which there does not exist any finite spanning set. Okay. Once again, let me make it clear. If there is a spanning set which has infinite number of vectors, that does not necessarily imply that the vector space is either finite dimensional or infinite dimensional. Okay, if there is no finite spanning set of that vector space, then that vector space is said to be an infinite dimensional one. So yeah, maybe can someone think of an example of a finite dimensional vector space and an example of an infinite dimensional vector space? Anyone?
Column space of any matrix.
That is a subspace, right? So in principle, you're right, but what is the vector space there?
R or Rn.
Rn. Is this a finite dimensional vector space?
Yes.
Yes. Why? What? Give me a spanning set of this, which is finite.
The columns of identity matrix.
Columns of identity matrix. Note once again, does not imply that all spanning sets of Rn are finite. For example, Rn itself is a spanning set of Rn because span of Rn itself is Rn. In Rn, of course, there's infinitely many elements. Example of an infinite dimensional vector space. Where is Bandhan these days? I don't see him. Anybody aware? Are you there, Bandhan? In the first several classes, Yadon used to ask or interact, but I don't see him these days. I hope it's fine. Right. Anybody else? An example of an infinite dimensional vector space? How about this vector space? Is it finite dimensional or infinite dimensional?
Infinite dimensional.
Infinite dimensional, right? Because you take any finite set, you can always, so finite set of this will contain polynomials. Since it is finite, there will be a maximum degree, right? And of course, you can come up with a polynomial with degree greater than that degree, which will not be spanned in the span by, or which will not belong to the span of this finite subset that you come up with. Okay, so therefore, this is an infinite dimensional vector space.
Sir, please show the definition of finite spanning set.
Sure.
So here you have written W is subset of V, means W
Yes.
not equal to V. So and
No, that's a type.
okay,
So it could be subset or equal to.
okay.
The issue is in LaTeX, which is the software I'm using for making these slides. When we just write subset, it is not, it just gives you this symbol. Okay? So that is why there is this code for subset and equal to, which is this, is this. So that is my typo. Okay. Is it clear to everyone that the set of polynomials forms an infinite dimensional vector space?
Yes, sir. R power Z will be an infinite dimension.
Yes. That our set is the set of doubly infinite sequences in a. And this also cannot be a finite dimensional vector space, and therefore it is an infinite dimensional vector space. Okay. Little L2, right? Square summable sequences in C. This also is an infinite dimensional vector space. Okay. So let's now define the other term that was in the title of the first slide, linear independence. Okay, so, and this, remember, we have already defined it in the context of matrices and vectors in Rn. We are now going to define this in general. Okay, so let V be any arbitrary vector space, and let W be a subset of V that contains n elements. Okay, we say that this set W is a set of linearly independent vectors if, we complete the definition, then can we say that this set W is linearly independent?
E1 V1 plus C2 V2 up to Cn Vn 0. If and only if all the C1s are Ci is 0.
Okay, so if there is a linear combination of these vectors that gives you not 0, but remember theta, right? Then all these scalars necessarily have to be the 0 scalars. Okay, this 0 is in the field. Okay, so the definition is just analogous to the definition of linearly independent set of vectors in Rn. The only change is, of course, instead of writing the additive identity as 0, we'll write it as theta. And all the scalars have to be the 0 scalar. Okay, that's the only difference. Now, whatever was the difficulty in the definition of span, the same difficulty lies over here as well. Right, and the difficulty is, how do I define an infinite set to be linearly independent? And now this you should be now able to answer if you have understood the analogous question in the definition of span.
All the set of the subsets of W are linearly independent.
No, you missed one
All finite subsets.
important
All the
adjective.
subsets are linearly. All the finite subsets are linearly independent.
Finite.
All finite subsets.
All linearly independent.
Right. All finite subsets of W should be linearly independent. Then we say that W is linearly independent. Yeah, again, I hope you see the difficulty here. There's no way that we can define an infinite linear combination on only vector space structure. We need something more. that you may or may not be able to cover in this course. Okay. Right. So for now, the set W is linearly independent, right? If all its finite subsets are linearly independent, and we have defined what is meant by a linearly independent finite set. The definition given in the slide. Can someone think of an example of an infinite set W which is linearly independent? And okay, let me give you a small hint maybe. The vector space that you should be looking for a subset in is, let's say, this. Can you come up with a subset of this vector space which has infinite number of elements, which is linearly independent as per the stated definition?
Sum of even power polynomials.
Sum of even powered polynomials. What is the subset there? I mean, all even power or even degree polynomials. Is that what you're trying to say?
Yes, sir.
How can that be linearly independent? So set of all even degree polynomials. So for example, this will also have x squared. It will also have 2x squared in it, right? Both of them belong to W, but are they linearly independent?
No, sir.
No, right?
Sir, miss here the coefficients AIs belongs to the field, right, sir?
Yes, yes. Yeah, so maybe I should specify here.
Sir, can
Okay.
we say that the subset Xi such that I belongs to Z?
What is xi?
X is to Y, X is to Y.
Acha, x raised to I. Okay. Yeah, so basically you are saying this.
Yes, sir.
Yeah, so good question. Is this linearly independent? Can you reason out aloud why
Yes, sir.
this is? Mhm.
Because x square cannot be written in terms of x cube, and so on. Miss in the terms of the terms which are not x square. Similarly, x is to I cannot be written in terms of x is to k, where k is not I.
Right, but
Because in
according
field,
to our definition, can you now show that?
uh, sir, suppose
Why
we take.
can't you write x squared in terms of the others? That is what basically this boils down to. And see, the difficulty in what you're stating is let's say you are able to show that x square cannot be written in as a linear combination of the remaining vectors. You'll also have to show x cube cannot be written. You'll also have to show x to the power 4 cannot be written. And of course, the list is endless. Can you think of a general argument?
Sir, suppose we take a subset uh, uh, x is to I1, x is to I2, x is to I3.
Okay, so let's say W bar be this subset x raised to I1 to x raised to
To
IN, right?
IN, where I1 and IN belongs to n.
Integers, right? P of finite natural numbers, right? Finite subset of W. Then
And if we assume that uh, A1 what A1 x raised to I1 plus A2 x raised to I2 and so on up to AN x raised to IN, that is equal to 0.
equal to 0. Yes, 0 is the zero polynomial.
Yes, 0 polynomial. Yes.
Then so when can you say two polynomials are equal?
Yes, when they all the terms are equal, all the terms in x and the power in the all the coefficients are equal of the
All the coefficients are equal, right? So this
implies all
implies
are 0. A1 is
exactly.
equal to A2 is equal to A3 and so on up to AN is equal to 0.
And that is what we wanted to prove, right?
Yes, sir.
Which and W bar was an arbitrary finite subset. Okay, we didn't choose a specific finite subset.
Yes, sir. Yes.
So therefore, if W bar is linearly independent, then W is linearly independent. Good. Okay. Is this clear to everyone?
Yes.
Okay. Right. So now, what is the relation between a spanning set and a linearly independent set, right? So what we now show is that in a finite dimensional vector space, the number of elements in a linearly independent set of vectors is always less than equal to the number of elements in a spanning set. And I hope it looks very intuitive and natural, right? But still we will try and prove this. The statement clear to everyone? Cannot have more linearly independent vectors than there are elements in a spanning set. Okay, proof is sort of easy. Let's look at the proof. Okay, since we are working in a finite dimensional vector space, of course, we'll have finite number of vectors in a spanning set, or there will be a spanning set which contains finite number of vectors. So let's assume that this U, which has n elements, is a spanning set, and let W be an arbitrary subset which has m elements such that W is linearly independent. Okay, so we are supposed to show that m cannot be greater than n. All right. Okay, so if I include the first element of my linearly independent set, is denoted by W1 over here, in the set U, what can we say about this set? Is this linearly independent or is this linearly dependent? Remember, U1 to UN spans the entire vector space V.
Linearly
Then this has to be linearly dependent, right?
Dependent.
Good. Right. So this is linearly dependent. So what can we say about the interrelationship between U's and W1? Right? What does linearly dependent mean? So there will
W1
be
can be written as a linear combination of
U's,
A,
right?
U, I's.
A1 on and A and UN. Now, can all these coefficients A1 to AN be zeros?
No.
Why?
Because the W1 is not non-zero.
Right. And why should that not be
Sir, because
zero?
if W1 were 0, then the set W will be linearly dependent.
Good. Right? So this is not possible. Okay, that all these coefficients are zero, because if they are zero, then W1 becomes zero, right? The additive identity theta, right? Uh, so, right. And any subset that contains theta, right? It cannot be linearly independent. Okay. So let's say there will be at least one coefficient, let's call it AJ, which is not zero. Okay, and in that case, I can write UJ, right, as a linear combination of the remaining elements. 1 to n, I not equal to j, but ej, k, I, and I. Agree? Okay, so there will be some vector uj for which aj is not zero. There can be more than that, but at least there will be one. Okay, uj. So therefore uj is in the span of the remaining u's and w1. Right. So what can we say about this set? What is the span of w1 and all the remaining u's? What will be the span of this set?
It will be equal to V.
Will be equal to V, right? So therefore we end up with a different spanning set. Okay, and the sort of important thing to note over here is the number of elements in the spanning set is still n. Okay, we have just replaced one u by a w. So the same thing can be done, right, by now including w2 in this spanning set, right? If I include w2 in this spanning set to get this set, this will also be linearly dependent, right? And if this is linearly dependent, there will be again some vector in the u's, let's say uk, right, such that uk will be in the span of the remaining vectors. Okay, so there exists a uk. The k of course is not equal to j. Uj is something we have already eliminated. Okay, such that uk is in the span of this set. And if uk is in the span of this set, we can eliminate uk and include w2 to obtain again a spanning set. Again, the number of elements in this spanning set is still n. Okay, is that clear to everyone? We are just replacing u's by w's. Okay, so since we are just replacing one element by another, the number of elements in the spanning set still remains n. Now the question is, can we have more linearly independent vectors than the number of elements in the spanning set? If we continue to replace U's by W's, and if there are more W's than U's, what will happen? After n iterations of this process of replacing, what is the spanning set that we'll end up with if m is greater than n? So after 2 iterations, we have W1, W2, but after n iterations,
till Wn.
till Wn, right? We'll end up with this set, which by construction should span V. Is that a problem?
Then W cannot be linearly independent.
Exactly, because if m is greater than n, then there is another vector Wn plus 1 in the set W. But since span of these n elements is V, Wn plus 1 will also belong to this span. It means W cannot be linearly independent. Okay, so this will imply that W is not linearly independent, and which of course is a contradiction. Okay, so same thing is available over here. So now let us define what is meant by basis. And basis is something that probably you have used earlier as well, right? Whenever you're doing, let's say, Cartesian geometry, you are using this concept already. But let us define it more precisely in an arbitrary vector space. Okay, and this particular definition that we'll be looking at is what is called a Hamel basis, which of course also means that there are other kinds of bases. But as far as this course is concerned, we'll only use the Hamel basis. Okay, so what is a Hamel basis? V be a vector space. Okay, I should emphasize this. We are talking about an ordered set. Okay, so let's say you have an ordered set beta that contains vectors from the vector space V put in a particular order. Okay, this is said to be a Hamel basis of the vector space V if beta spans V and beta is a linearly independent set of vectors. So it should span as well as it should be linearly independent. Only then we get a Hamel basis or just a basis. Is the definition understood?
Sir,
Yes.
so what would be the significance of ordered thing? Because span definition and definition of linear independence both have addition, which is commutative. Then, like,
Right. Yes. So in principle, let's say I have this set, right? V1, V2, Vn, and let me define another ordered set. So as sets, say Vn and some particular different order. So as sets, beta and beta 1 are the same, but as ordered sets, they are different. So one thing I'll tell you why it matters is, okay, so there is a small concept that I'll have to introduce before I justify this. Give me just a second. Right? Why is this ordered? I'm going to discuss in 2 parts, one right now, one hopefully in the next class. Okay. So, but apart from that, is everything else clear about this definition?
Yes, sir.
Okay. So, can someone first give me examples of vector spaces and their bases? So let's start with the simplest case where the vector space is R. What would be a basis? R over R. Let me specify that also. So I am asking you to find a subset of R which spans R and which is linearly independent. Can you think of a subset?
1.
1. Any other subset?
All numbers apart from 0.
All numbers, so are you saying
Means,
this?
no.
No, okay.
Different sets.
Acha. So any singleton set
Yes.
which contains an element apart from 0.
Yes.
Okay. So it could be A where A is not equal to 0. Is clear to everyone? Because if you have a 0 there, then it does not form a linearly independent set, right? And of course, it also doesn't span. But as far as any other non-zero number is concerned, right, you can use that number to span the entire vector space R. And just one non-zero number, of course, is going to be linearly independent. Let's look at another example, something that all of you would be familiar with right from your school days. R2 over R. Give me an example of a basis.
1 0 0 1.
1 0 0 1. And so this is what is called the standard basis, the X and Y axis, which is what you have been using with. But is there any other basis of R2?
Any two linear independent vectors.
So yeah, something like this. Okay, let us. Right, so I mean the important conclusion here is although we always use the X and Y axis, right? That's not necessarily mandatory. So maybe this would be more evident if I draw a picture. Right. So these are your usual bases, unit vector in X and unit vector in Y. But in principle, this and this also is a basis. Okay, because they are linearly independent and they span R2. Okay, so that I hope is clear. Let us look at more examples before I talk about the significance of order. How about C over C? What is the basis here?
So 1 and I cap. 1 and J.
1 and J. How many of you agree with this?
Yes, sir. Agree.
Okay. Okay. Let's just examine this particular basis. If you're saying this is a basis, this should be linearly independent, right?
Yes, sir.
But J can be written as J scalar multiplication 1, isn't it?
Yes, sir. Yes, sir. Then it is not a basis. Yes.
Exactly. So this is not linearly independent. Why? Because remember the field over here was explicitly written that the field is C. So you can pick scalars, any scalar from the field. Here chosen is j or square root minus 1. And therefore, this is not linearly independent. So eta is not a basis. Can you give me an example of a subset which is a basis?
It can be any non-zero complex number.
Any non-zero complex number. Oh, Vandan, you are back. It is not zero. Forms a basis. Okay, the important thing to remember is the scalars that you can pick can be any complex number. So therefore, any complex number, let's say a plus bi, or b, let me use a different general notation, c plus di is nothing but c plus di divided by a into a. Okay, so this is just a scalar multiplication with the chosen vector a. So therefore, this forms a basis. How about C over R? You come up with a basis.
1j.
1j.
1j. Okay. This forms a basis. They are linearly independent because you're not allowed to pick complex valued scalars. Okay, so you will need these two vectors as a basis. One final, maybe a couple of more examples, and then we'll discuss about the orderness of need of order in this set. PR, set of polynomials. What would be a basis here? Some sense we know the answer already.
Sir, x is 2i such that I belongs to n.
X.
Right. This is a basis because you've already shown that this is linearly independent. Give me any polynomial. By definition, polynomial has to have a maximum degree, right, or order. You just keep getting confused with the definitions there. And so you can write it as a linear combination of finite number of elements from this set. Okay, so therefore it spans PR. One more example and then we stop there. Set of all or vector space of all m cross n matrices over real numbers. What could be a basis here?
Identity matrix of M cross N.
It's only one.
Yes, sir. It will have m times n bases.
Okay, which ones? Can you think of an example of basis?
At every position, we will put one, and everywhere else we will put zero.
Okay, so these matrices in general will be denoted by delta PQ, where delta PQ m comma n is equal to 1 if m is equal to p and q is equal to n, otherwise 0. Okay, so set this, set p, set n, set q, set n. Okay, remember, basis is a subset of the same vector space, so its element should be of the same nature as the elements of the vector space. Okay, so in this case, the vector space elements are m by n matrices. So the bases also have to be m by n matrices, right? And
Sir,
then yes,
how does beta span m?
beta spans m. Okay, so let's take an arbitrary matrix in this vector space, right? Okay, so I will denote the ijth entry of A by Aij, and then I goes from 1 to m, j goes from 1 to n. Okay,
Yes, sir.
so then I hope you see this can be written as summation over ij, I going from 1 to n, j going from 1 to m, aij, where aij in this notation is just a scalar, okay, the real number aij times delta ij.
Yes, sir. Yes, sir. Now it is clear, sir.
Anybody else has doubts here?
Yeah, I from 1 to m.
I from, oh yeah, thank you. 1 to m and j should be from 1 to n. Thank you. Right, so now let's look at the ordered property here, right? And for that, let me talk about representation of vectors in a basis. So you must see, some of you possibly are wondering what is the importance of basis, right? Is the definition is one thing, but why is this concept required at all? Right, so can some of you think aloud upon this? What is the importance of basis? If I give you a basis set beta of V, what can we do with this?
Means, sir, it is a minimum information that contain we can represent whole vector space.
Whole vector space, right? So if I take an arbitrary element V in the vector space, because I have a basis beta, I know that I can write V as a linear combination of elements in the basis beta. So if I were to denote, let me choose another notation. Let's say beta is V1 to Vn. Okay, then I know that this is true. Right? Now, is it possible to write V also as some different linear combination of the same elements?
No, sir.
No, sir.
No. Why?
If it's true, then V1 to Vn are not linearly independent.
Exactly. Right. So this would imply that E1 minus C1 V1, so on and so forth, an minus cn vn could be theta. And since we have assumed these linear combinations are distinct, there exists at least a particular j such that aj is not equal to cj, which implies that beta is not linearly independent. Which means that for every element V in the vector space V, beta gives a unique linear combination. Right? That clear to everyone? So then, if for a particular element V, I have this linear combination in terms of the bases, we can assume that the bases beta are fixed. Right? You can arbitrarily choose beta, but once you have chosen, I'm going to assume that beta are fixed. In that case, if I want to represent or communicate this vector V, right, instead of writing this vector, I can also just give you the list of scalars. These scalars will come from, they'll form a column vector, which will, of course, belong to Fn. This is what is called representation of V, the vector, in the basis beta. And at least for my course, I will denote this column vector by this notation. This is the vector V, which is being represented in the basis beta. So in principle, the conclusion is, since that this representation is unique, right? If I want to communicate V, I can also do the same by communicating this set of n numbers or n elements of the field, right? And if you think about the way Cartesian geometry works, you have been using this, isn't it? If I want, this is, let's say, my R2. This is R2. If I want to convey the location of a point P in R2, how do I do that?
Two coordinates, x and y.
Two coordinates or two numbers at least, right?
Yes.
Remember, these two numbers are not the point. It is a representation. Right? And by default, we have always been assuming that this first number is the x coordinate, the second number is the y coordinate. But in principle, there is nothing special about this choice. Right? So what this means, this two numbers, P1, P2, it's what you're basically saying is this is P1 times the x unit vector plus P2 times the y unit vector. This is analogous to this. Okay. Put both of them in red so that you see the similarity. Okay, so the importance of the basis is that it affords unique representation. So now think about this situation. Is this clear, by the way? The importance of basis?
Yes, sir.
Okay, so now let's say instead of P, I'm giving you these two numbers, P1, P2. And now you again want to figure out what was the original point. How will you do that? How will you go from here to here?
P1 into first
First,
V1.
I mean, I think that is important. Why is it this and why not this? And are both of them the same?
Not same.
They are surely not the same, right? So how do we understand that this P1 is the coefficient to be used for the first basis only and not for the second basis?
In the order they are written.
Order. Okay, so in summary, I hope you understand that the order is important. We'll sort of risking here by taking an example from your signals and systems course. So by now, all of you know this exponential Fourier series.
Yes.
Yes, the coefficients are usually called C0, C1, C minus 1, etc. Right? I don't know if you have used a different notation.
We use AK.
AK, okay, so that is the notation. So C of t is summation k going from minus infinity to infinity AK e to the power j k omega 0 t, right? And what this says is, if I want to convey this signal, I can convey it either this way or I give you AKs. Yes? I hope this is familiar. If not, then I'm going to skip this for now.
Yes, sir.
Please feel free to stop me from mentioning signals and systems in this course. Right? It's just that for me, I mean, both of them are so close together. I want you to also see that. I want you to see this resemblance. If you're sort of convinced with this, and if I want to get back what is my CT, how do I know that A0 has to be sort of multiplied to e to the power j0 omega t? Not because of its coefficient, I mean the subscript 0, right? In practice, this will be replaced by some actual real number or a complex number. And how do you know that complex number is associated with this complex valued function and not with e raised to j omega 0 t? You know that because these functions are also put in a specific order. Okay?
Yes, sir.
Okay. So now let's look at some results based on this, on the basis. So the next proposition states that as far as we have a finite dimensional vector space, every finite spanning set can be reduced to a basis. Does that look intuitive to everyone? If V is a finite dimensional vector space, let's say U contains n elements such that span of U is V, right? I can reduce U to form a basis of V. How will I do that?
Removing the some vectors which are linearly
Dependent, right? Okay, so I think you can write this yourselves. The basic idea is remove linearly dependent elements from U, sorry. Okay, since you are removing only linearly dependent elements, the span of the remaining elements is going to be the same, which is V. Okay, so the spanning property is maintained. All you are doing is you're trying to obtain a linearly independent set. Okay, so that I hope is evident. So let's get into this. Next proposition is an implication of proposition 6 and 7. Right? It says that every finite dimensional vector space has a basis. Okay, that again is evident. Why? Because what is the definition of a finite dimensional vector space?
it has a finite spanning set.
As a finite spanning set. And then from proposition 7,
This can be reduced to a finite base.
exactly. Okay, so that is proposition number 8. Last proposition in this series is that any set of basis vector of a vector space contains the same number of elements. So again, if you have noticed in all the examples of vector spaces and their bases, yes, the choice of basis is not unique, but in all bases that we saw for a particular vector space, the number of elements had to be the same. How do we show this? So let alpha and beta be a basis of my vector space V. Let cardinality of alpha be n and cardinality of beta be m. And let's assume without loss of generality that n is greater than m. So, or let us just show that n is equal to m. How do we show that? So span of alpha is V, beta is linearly independent. What does that tell us? Proposition 6. The number of linearly independent vectors has to be less than the number of elements in a spanning set, right?
Yes.
M has to be less than equal to n. Similarly, span of beta is also V and alpha is linearly independent. Therefore, n has to be less than equal to m, which of course implies m is equal to n. Okay, so this is an important conclusion. So choice of basis vectors is not unique, but no matter what basis you choose, the number of elements in a basis always has to be the same. Okay, this is an important property of a vector space, and this is what is called the dimension of a vector space. Okay, so if V is a finite dimensional vector space, then for any choice of basis vectors, the number of elements in that basis set is called the dimension of the vector space. All right, is that understood?
Yes, sir.
Okay, so what is the dimension of R2?
Sir, 2.
2, right? almost a stupid question. Now you see that dimension of R2 is 2 not because of these two, but I mean the definition now says that it should be 2. Okay, what is dimension of C over C?
1.
1.
Yes, sir. 1.
Dimension of C over R?
2.
2. Okay, so be careful with
Sir,
this.
dimension of R2 over C is 1.
Is R2 over C a vector space?
So this
No,
scalar multiplication will not be closure then.
Exactly. So not a vector space, and therefore its dimension doesn't arise. Okay. Okay, so I think with this, it is a logical conclusion to one section of our linear algebra portion. In the next class, we are going to look at linear transformations, okay, which is sort of the, if there is a core that I wish to cover for this part of the course, it is linear transformations. Okay, so that is what we'll start from the next class. For now, all of you have to attend a quiz, which is just it should now be available on the course web page. There are 5 questions in the quiz, and you get 10 minutes to attempt those 5 questions. I think the last time for attempting is 9:55. So the quiz will close at 9:55 sharp. Okay, irrespective of whether you have received 10 minutes or not. So I think it's good that you start attempting that quiz now.
Sir,
Yes.
sir, I have a project related doubt.
Right. So I will be available at 9:55 in the same meeting room.
Okay, sir.
So we'll discuss there. Once again, please start attempting the quiz. It should now be visible on the course web page. If somebody could confirm that, that will be great. Although it is written that it will be available till 9:50 a.m. only, I've just changed that. It will now be available till 9:55 a.m. Of course, you get 10 minutes to attempt the quiz.
Yes, sir, it is visible.
Okay, thank you and all the best.